Hello again. Thank you very much for joining us on this webinar today. And you are welcome to this webinar titled Organic Agriculture, Mitigating and Adapting to Climate Change Through Carbon Sequestration. My name is Philip Osenhensen, and I am a postdoctoral research associate here at Rodale Institute. The purpose of this webinar is to give you insight into soil organic carbon accumulation potential of organic agriculture, leveraging Rodale Institute's farming systems trial. Alrighty, so here is an outline for my presentation. So today I will discuss climate change and its consequence, rising atmospheric carbon dioxide levels, and US greenhouse gas emissions. And I'll talk about soil, using soil as a weapon to fight climate change. And I'll touch on organic agriculture, and I'll finally talk about FST results, and I'll have the opportunity to answer or try to answer any questions you may have. So believe it or not, climate change poses the greatest threat to humanity and therefore demands immediate action or immediate and coordinated actions by all individuals and by all countries. Climate change can simply be defined as a long-term shift in temperature and weather patterns. Since 1800s, human activities have been the main driver of climate change, primarily due to the burning of fossil fuel. And the consequence of climate change is more evident now than ever before. As I speak to you now, I'm in Pennsylvania, and we are having our fair share of the wildfire smoke from the Canadian wildfires. If you are somewhere on the East Coast, you might, or you may have experienced this already. So the effects of climate change include severe droughts, flooding, severe wildfires, melting ice sheets, rising sea levels, ocean acidification, and many, many more. We know that there are a lot of greenhouse gases in the atmosphere: carbon dioxide, methane, nitrous oxide, chlorofluorocarbons, and many other fluorinated gases. But by far, the largest contributor to climate change is carbon dioxide. Carbon dioxide is the most abundant greenhouse gas in the atmosphere, accounting for nearly 80% of the total greenhouse gas emissions in the US in 2021. And this is according to the EPA. So you can say that carbon dioxide, or atmospheric carbon dioxide, is the primary cause of climate change. And as you can see from this graph, the level of atmospheric carbon dioxide is increasing, but it is not only increasing, it is increasing at a much more faster rate than before. So for example, when the National Oceanic and Atmospheric Administration, or NOAA, started measuring atmospheric carbon dioxide in 1957, the rate of increase was about 0.5 ppm per year during the first 10 years. So that is evident. You can see from this slope that we have relatively mild slope. But in the last few decades, or in the last 2 decades, the rate of increase in carbon dioxide is about 2.3 ppm per year. This is a very disturbing or worrying statistic or facts. Speaking about disturbing stats or facts, did you know that on April 7th of this year, atmospheric carbon dioxide levels reached an all-time high at 423 ppm. This is the highest level ever recorded in human history. So in my lifetime, I'm in my early 30s, and in my lifetime, atmospheric carbon dioxide levels has increased by more than 60 ppm. So the carbon dioxide levels are now 50% higher than pre-industrial levels, and the average temperature of the Earth's surface is about 1.1 degrees Celsius warmer than before industrial revolution. And we know that there is a strong correlation or relationship between rising atmospheric carbon dioxide levels and global temperatures. So the last decade, which is from 2011 to 2020, was the warmest on record. And each of the last 4 decades have been warmer than any previous decade since 1850. This graph shows US greenhouse gas emissions over the years. The rusty orange line represents total greenhouse gas emission, and that represents the total amount of greenhouse gas produced or released into the atmosphere. The dark gray line represents net emission, which is the difference between the total greenhouse gas or the total amount of greenhouse gas produced or released into the atmosphere and the total greenhouse gas emissions removed from the atmosphere. So the difference between these lines represents or gives you an indication of the total amount of greenhouse gas removed from the atmosphere. And as you can see from this graph, there hasn't been much improvement in the total amount of greenhouse gas removed from the atmosphere. So this tells us that we have work to do. We need to make this gap wider. We need to remove more carbon dioxide or greenhouse gases from the atmosphere. So since 1990, the total greenhouse gas emission has decreased by about 2%. The dip you see in this total greenhouse gas emission in 2020 was as a result of the impact of COVID-19, leading to impact of COVID-19 that impacted like travels and economic activities. But as you can see from the graph, right after economic activities, after lockdown and economic activities started booming, the rates or the increase from 2020 to 2021 is now 5%. This clearly indicates that there's a strong relationship between human activity and greenhouse gas emissions. Electricity generation, transportation, and industry sectors are the 3 primary sources of greenhouse gas emissions over the years. And these sources account for 70 to 75% of greenhouse gas emissions. The only sector that acts as a sink or a net sink for greenhouse gas emission is land use and the forestry sector. So since 1990, the forestry sector has acted as a net sink, which means that that sector absorbs more carbon dioxide from the atmosphere or removes more carbon dioxide from the atmosphere than it emits into the atmosphere. So in 2021, the land use and forestry sector offsetted about 12% of the total gross greenhouse gas emissions in the US. Agriculture contributes about 10% to the total greenhouse gas emission in 2021. This number is a drop from 2020, which was about 11.4%. So now USDA has invested a lot of money into climate smart projects to investigate ways to reduce greenhouse gas emissions as a result of or from agricultural practices. The major agricultural practices or some of the agricultural practices that lead to an increase in greenhouse gas emissions include livestock enteric fermentation. And this is the process whereby a microbe or a microorganism in the rumen of ruminants breaks down carbohydrates into simpler form. So during the process of breaking down carbohydrates into simpler form in the rumen of ruminants, they produce a lot of methane, or methane is a byproduct of that natural process. So livestock enteric fermentation is a major source of methane production, and rice cultivation is also a major source of methane production. So, rice is grown in flooded areas, which is an ideal opportunity for anaerobic bacteria to produce methane. So the use of fossil fuel combustion from agriculture equipment also contribute to carbon dioxide emission. And fertilizer and manure application are major source of nitrous oxide emission. So agriculture is the largest source of nitrous oxide emission in 2021, accounting for about 75% of the total nitrous oxide emission in the US. We cannot fight climate change without using soil as our weapon. And the reason I say this is because soil is extremely important, or it plays a critical role in the global carbon cycle. Soil has huge or massive amounts of carbon. The amount of carbon in soil is more than the amount of carbon in the atmosphere, plus the amount of carbon in global vegetation. In fact, it has been estimated that if you take a meter deep soil, the amount of carbon in a meter deep soil is 1,550. And this number, or this amount, 1,550 petagram. And this number is 2 times higher than the amount of carbon in the atmosphere, and nearly 3 times the amount of carbon in vegetation or global vegetation. So what this tells you is we have a lot of carbon in the atmosphere. And keep in mind that 1 petagram is equivalent to 10 to the power 15 grams. So 1,550 petagram of carbon is equivalent to, or is equal to 1,550 billion metric ton of carbon. That is a lot of carbon in the soil. So with soil having such huge amounts of carbon, small changes in carbon in the soil can drastically or significantly affect global carbon cycle and also the concentration of carbon dioxide in the atmosphere. It is also worth mentioning that although we know we have huge amounts of carbon in the soil, we also know that our soils have the capacities to store more carbon. We know this because our soils have been overexploited since the dawn of agriculture, which was about 12,000 years ago. Jonathan Sandeman in 2017, Jonathan Sandeman and his colleagues in 2017 estimated that the conversion of natural systems to agricultural systems resulted in the loss of about 133 petagram of soil organic carbon from the top 2 meters. So what this does is it gives us the opportunity to change the way we manage our agricultural land using regenerative practices to put back this lost carbon into the soil. We can put back this lost carbon into the soil through a process called soil carbon sequestration. And soil carbon sequestration is a viable climate change mitigation strategy. So soil carbon sequestration simply means or it involves plants absorbing atmospheric carbon dioxide through the process of photosynthesis and pumping this carbon dioxide into the soil. So soil carbon sequestration increases soil carbon content, and it is governed by a delicate balance between inputs, such as photosynthetic inputs via litter and root exudation, and outputs, such as decomposition. So to enhance soil carbon sequestration, we need to maximize carbon inputs. And we can maximize carbon inputs by increasing biomass input into the soil. And we can minimize carbon outputs from the soil by minimizing tillage or minimizing soil disturbance. So to simply put, to maximize carbon inputs, we need to increase our biomass inputs into the soil. And here are some of the ways we can increase biomass input into the soil: through cover cropping, crop rotation, adding perennials, intensifying crop livestock integration. And at the same time, we also need to minimize soil disturbance. So if we minimize soil disturbance, we reduce the oxidation of carbon from the soil. So you have to make sure your input is much, much greater than your output for you to sequester carbon. We know that increasing soil carbon is critical to fighting climate change, but not only that, it is also important to global food security now and in the future. An increase in soil carbon improves crop productivity and quality, and it also improves the profitability of producers. So an increase in carbon, which is also improving soil health, has so many other benefits or co-benefits, such as water cycling and quality. So water filtration and purification, improving erosion control and flood regulation, nutrient cycling, habitat and biodiversity, and many, many more. So soil carbon sequestration is essentially a win-win strategy for humans, for producers, for consumers, and also for our environment. You know, unlike conventional farming, organic agriculture or organic farming avoids the use of synthetic pesticides and synthetic fertilizers, but instead relies or utilizes carbon-based amendments such as animal and green manure, and also employs ecological practices such as cover cropping and diverse crop rotation in a holistic approach to improve the performance of the system. So organic farmers tend to have longer crop rotation and more diverse cropping systems than conventional farmers. This is because organic farmers need to utilize cover crops and crop rotation to break weed and pest cycle, as well as to optimize nutrient cycling. But tillage is the Achilles heel of organic farming, as many organic farmers rely heavily on tillage for weed control. We know tillage or frequent use of tillage destroy soil structure and leave the soil prone to erosion, as well as negatively affects soil health and negatively affects many soil health parameters, including soil organic matter. And we also know that in organic systems, we cannot completely eliminate tillage at this point in time. But what we know is we can reduce tillage. And here at Rodale Institute, has been at the forefront of promoting reduced tillage in organic systems using the roller crimper. So the organic industry is rapidly growing in many fronts. In the consumer demand front, from the market front, the areas under organic farming. So if you look at multiple sectors within the organic industry, everything is growing. So for example, area under organic in 2000 globally has increased by over fivefold, from 50 million hectares to about 76.4 million hectares. You can see there has been significant and very drastic growth. But at 76.4 million hectares, this just represents only 1.5% of the total global agricultural land area. So although we are growing, which is good, but it's still small. It's just 1.5% of the total global agricultural area. And this number in the US is much lower. In the US, the area under organic is about 2.3 million hectares, and it represents only 0.6% of the total agricultural land in the country. So this calls for the need for improvements. Like, we need more areas under organic farming. Rodale Institute has the farming systems trial, which is a long-term experiment which was started in 1981 to compare organic and conventional cropping systems. So with the farming systems trial still running, it is the longest side-by-side comparison of organic and conventional green cropping systems in North America. The farming systems trial has contributed immensely to the organic industry in the United States. For example, if you are familiar with the Organic Food Production Act, that act was enacted in 1990. That was 9 years after the farming systems trial was established. And the farming systems trial contributed immensely in developing that act. The farming systems trial sits on a 6-hectare farmland located in Kutztown, Pennsylvania, which is where the main campus of Rodale Institute is. So Kutztown, Pennsylvania is about 2-hour drive west of New York City and about 1-hour drive north of Philly. So in 2021, we released our 40-year report, or the 40-year report for the farming systems trial. And the image you are seeing on the screen is the farming systems trial. So here are some other area images of the farming systems trial over the years. So farming systems trial in 1992, farming systems trial in 1999, and farming systems trial in 2000, and finally, farming systems trial today. So in the farming systems trial, there are 3 cropping systems: conventional, organic legume, and organic manure. And these systems vary in cash crops, cover crops, and inputs. So the conventional system follows a 3-year rotation, which is corn, soybean. There's no cover crop in that system. So this simple rotation is practiced by most or many producers in the Mid-Atlantic region. And we are using corn and soybean because they are the 2 major grains produced in the US. The total cropland under grains in the US is about 100 million hectares, and corn and soybean is produced in about 70 million hectares of that. So almost 70% is under corn and soybean. So you can't have a conventional system without having corn and soybean in it, which are the 2 major cash crops. There are no cover crops in the system, like I said, and this system heavily relies on synthetic inputs, synthetic pesticides, and synthetic fertilizer. Then we have the organic legume system, which follows a 4-year rotation of corn, oats, soybean, wheat. And in this system, we have cover crops, rye, and hairy veg. I must say that during the oat phase, we interseed with clover. And in this system, there was no input. So we rely solely on biological nitrogen fixation from the legumes. So you know that our Earth atmosphere has about 78% of nitrogen, but most plants cannot utilize the amount of nitrogen we have in the atmosphere, except only few or specialized plants like legumes. So legumes are able to form a symbiotic relationship with rhizobia or bacteria in the soil to break down this strong nitrogen bond and make nitrogen available for plant use. So we solely rely on biological nitrogen fixation in the organic legume system. The manure system is much, much longer and diverse. So on top of the 4-year rotation in the legume system, we have a 3-year hay phase and a corn silage phase, as well as wheat. So the manure system is a 9-year rotation. The 3-year hay phase consists of alfalfa and orchard grass. And we have rye and hairy veg as our cover crop in this system. And we apply composted manure in this system. So during the 9-year phase, we apply composted manure during the oats phase of the rotation and during the corn silage phase of the rotation. So during the 9-year phase, we apply composted manure only 2 times at rates of about 10 to 15 tons per acre. So as I said or mentioned in the previous slide, the farming systems trial was established in 1981, and in 2008, a major modification happened. So prior to 2008, the farming systems trial was under intensive tillage. All plots were under intensive tillage. So in 2008, the modification that happened was the 3 systems were divided into full tillage and reduced tillage. So we introduced the tillage treatments in 2008. But we know reduced tillage is achieved in a different ways in conventional and organic system. Because in conventional system, you can use chemical-based herbicides and GMO seeds to achieve reduced tillage. But in organic system, we don't have that tool. So we do what is called rotational no-till or cover crop-based rotational no-till. So what that means is we will use tillage to establish our cover crop sometime in the fall, then simultaneously terminate the cover crop mechanically using the roller crimper, and also plant our cash crop into the mulch simultaneously. So this is the result. So you can see here, cover crop residue become a weed suppressing mulch, and you can see, so this cover crop is rye, and you can see your soybean. So to get into some results, when FST started in 1981, the soil organic matter levels were relatively similar. So soil organic matter can be used as a proxy for soil organic carbon or soil carbon, because soil organic matter contains 58% carbon. So you can see that in 1981, the 3 systems had relatively similar soil organic matter, but the 2 organic systems increased rapidly in soil organic matter. So in 1998, Drinkwater et al. Published a paper on FST soil organic carbon stock from 1981 to 1995. And they found that the percent increase in the manure system from 1981 to 1995 was about 30%. And the percent increase in the legume system from 1981 to 1995 was about 14%, and it was significant. But the percent increase in the conventional system was only 7%. So this kind of gives you an idea on or about this soil organic carbon sequestration potential of organic farming. So the primary reason for the increase was as a result of crop diversification, like diversified cropping systems and cover cropping. So in 2021, we wanted to accurately estimate soil organic carbon stock in the entire 1 meter soil profile. So we know that deep sampling is essential when you want to accurately estimate soil organic carbon, because if you just consider the topsoil, you might underestimate or overestimate your soil organic carbon, and therefore you might underestimate or overestimate your soil carbon sequestration potential. So in 2021, we collected a meter deep soil and we sliced it into 5 depths, 0 to 10, 10 to 20, 20 to 30, 30 to 60, and 60 to 100 centimeters. And we measured soil organic carbon for each depth, as well as the cumulative soil organic carbon for the entire profile, 1 meter profile. And we found out the 2 organic systems had significantly more soil organic carbon stock at the depth of 0 to 10 than the conventional system. And even if you consider 10 to 20 at this depth, the difference is much, much greater. Then 20 to 30, the 2 organic systems outperforming the conventional system. And even at a depth as deep as 30 to 60, the manure system significantly had higher soil organic carbon stock than the conventional system. And when it comes to climate change, soil or carbon in the subsoil are very important because those carbon in the subsoil are not susceptible to losses, unlike soil in the topsoil, because your topsoils will be susceptible to losses as a result of mineralization by microbes, erosion, and many other things. So the soil or carbon in the subsoil is very, very important for long-term carbon sequestration and stabilization. So from 0 to 30, we found that soil organic carbon stock was almost 40% higher in the 2 organic systems than the conventional system. And from the depth, or at 30 to 60 centimeters, we found that soil organic carbon was 17% higher in the 2 organic systems than the conventional system. So when we aggregated the entire soil sample from 0 to 100, what we are seeing is the soil organic carbon stock in the legume system was 23% higher than the conventional system. And the manure system was 40% higher than the conventional system. And the reason we are seeing higher soil organic carbon stock in the topsoil is because of long-term ecological practices in the organic system, such as crop rotations, cover cropping, and or compost addition. What is most striking about this graph particularly is the fact that in the manure system, remember, in the legume system, remember, there's no carbon input. We don't add compost or manure in that system, yet it is able to outproduce the conventional system. And the primary reason for that is diversified cropping system and crop rotation in that legume system. So the primary reason for this increase in soil organic carbon from 0 to 100 is as a result of long-term ecological practices such as cover cropping, crop rotations, and manure input in the organic systems. Now, surprisingly, we didn't see the effects of tillage on soil organic carbon stock. So as you can see, full tillage, our soil organic carbon stock was about 80 megagram per hectare, and at conservation tillage, almost the same. And the reason we didn't see the effects of tillage on soil organic carbon stock were topography and high baseline soil organic carbon stock. So we know that we tend to lose soil as a result of erosion. And with FST, or the farming systems trial, the slope of FST is relatively flat, like 1 to 3%. So we don't lose carbon as a result of water erosion. And where FST, we don't lose carbon as a result of water erosion. Another major factor that contributed to the lack of difference in tillage practices is as a result of the high baseline of soil organic carbon stock. So prior to tillage implementation, or prior to implementing tillage as a treatment in the farming systems trial, soil organic carbon levels were already high across all systems, as I showed in the soil organic matter graph. The soil organic carbon levels were already high. So our conservation tillage could not drastically improve or significantly improve the soil organic carbon level, which was already high. So this shows that the effects of tillage is highly site specific, and it depends on so many factors. It depends on so many factors, and it's very, very contextual and depends on management and site-specific characteristics. So far, I've been talking a lot about climate change mitigation and soil organic carbon sequestration and so many other things. But now I want to draw your attention to how the different systems in FST perform under drought condition. So drought condition to me is a measure of resilience, so how resilient these systems are. And it also shows how adaptive the system is to climate change, because we know one of the major consequences of climate change is severe droughts. So in the history of the farming systems trial, we had moderate droughts in 1988, 1994, and 1998. So during this period, corn yield in 1988 across the three systems, where you could say were higher in the organic system, 92, 93 in the manure system, and 80 bushels per acre. The red color represents bushels per acre, the black represents kilogram per hectare. In 1994, you can even see a much, much bigger difference between the conventional system and the two organic systems. In 1998, you can see the legume system at the highest, followed by the manure system, and finally the conventional system. In 2016, we had only 9 inches of rain from June 1st to August 31st. And given our location, that's an extremely dry year, because we get about 1 meter of rain annually. And during the corn production season, we get about 23 to 29 inches of rain during the growing season for corn. So you could see the performance of the different systems under such dry year. So the two organic systems outperform the conventional system. And again, this shows how resilient the soils in the two organic systems are. So these soils are able to remain moist even though environmental conditions, or even though environment is very dry, which is a valuable characteristic in the face of climate change. You need to have soils that have the ability to remain moist when the environment is dry, and remain dry when the environment is extremely moist. So with that, I would like to acknowledge this many scientists and many individuals who have worked on the farming systems trials over the years. And importantly, I would like to acknowledge our funding agencies, William Penn Foundation, TOS, Sustainability Foundation, for providing funds for this study and for supporting works or research activities at the farming systems trial. Thank you very much for your time and for your attention. I would be glad to answer any question you may have. Thank you. So I have a question here. What type of manure was used in the manure system of the 40? We use, so the manure system tries to mimic dairy farming, like what dairy farmers would do. So we use composted dairy manure in the manure system. So if you have dairy cattle on your farm, we try to mimic how that scenario pans out. Yeah, so we use composted dairy manure in the manure system. I have another question, and the question is, what's the soil type of the farming systems trial? So the farming systems trial, the soil type is silt loam. Silt loam soil is the soil type of the farming system trial. And I have another question on whether we have any studies on perennials or other tree crops. Rodale Institute now, we have a perennial scientist. She joined the team about a year ago, and she's now working on perennials and tree crops. I have a question. Continuing conventional practices on your farm only perpetuate and contribute to the program. It is time to stop. We can't stop the conventional system in the farming systems trial because it gives us an opportunity to compare the performance of the organic system to the conventional system. So after 40 years of the farming systems trial, we don't know. So we don't know how the system will work. We still need to compare the different systems in the farming systems trial. Yeah, so even after 40 years, we still have more like different research questions. So now we are even looking into water quality. So the effects of different cropping systems, conventional and organic, on water quality. So there are still more interesting research areas to look into. So having the conventional system, gives us an opportunity to have a side-by-side comparison. Oh, so in 2016 slide, what do RT and FT stand for? So RT stands for reduced tillage and FT stand for full tillage. Do you have a schedule available of what was done and when for the legume and manure system? So prior to the establishment of the farming systems trial in 1981, the field was managed intensively under conventional system. So the entire 5 or 6 hectare farmland was managed intensively under conventional system. I think it was under wheat production. I have another question on, so dairy produces methane versus how much carbon is sequestered in the ground. Is it worth it? Yeah, this is a much difficult and complicated or complex question. It's hard to say. The global warming potential of methane is much higher than carbon dioxide. It's about 25 times higher than carbon dioxide. So it depends. The answer to this question is it depends on how much methane you are producing and how much carbon dioxide you are able to sequester. So like I said, or like I mentioned during my presentation, is the balance. So is your inputs much higher than your outputs? That's what we need to reduce the effects of climate change or mitigate climate change. So provided your inputs, which is when provided you have the ability to sequester or remove more carbon dioxide from the atmosphere than the amount of carbon dioxide you are putting into the atmosphere, then yeah, that should be good. So again, I would like to thank you all for your time and attention. And thank you very much for participating in this webinar. I enjoy the rest of your day. Have a great day. Bye.